Okay, let's see what's going on today. Today we're talking about odd and even functions. Okay, we're going to look at them graphically, we're going to look at them numerically, and then we're going to look at them analytically. So we're going to analyze them using algebra, which is always the most fun. Okay, so like it says in geometry, we had two types of symmetry: reflective symmetry and rotational symmetry. So looking at these graphs here, like look at F. What type of symmetry do we notice with the graph of F? So this graph has reflexive or reflection symmetry. Right? I can draw a dashed line right down the middle of this graph, right here along your y-axis. And if I fold it along that y-axis, okay, hopefully you can see with your eyeballs that each of these points would line up exactly and correspond with their neighbor on that side. Okay, this is a reflectional symmetry. Reflection across the y-axis. Okay. What about this one? What type of symmetry does this have? Can I fold it or do I have to spin it? Spinning it, right? So let me see if I can spin it. If I take this graph like here and I make it do a 180, does the graph look exactly like how it started? Does this graph right here look exactly like this graph right there? Yes, it does. So this is our example of some rotational symmetry. And we're rotating this point right around the origin. If you keep your paper still and you spin it, we have rotational symmetry. Okay, so this one is rotational, and it's rotational about the origin. Okay, so we can do a similar thing for all of these and talk about their symmetry. So here is your symmetry. Okay, and we'll notice here, look at this reflectional symmetry. What about the points? What are happening to these x and y values when we have reflection symmetry? Okay, this point is 1, 3. This corresponding point is -1, 3. This point is 2, 0. This corresponding point over here is -2, 0. Right, so if we're looking at the x and the y values at each of these corresponding points, what do you notice about the y values? The y value over here compared to the y value over there. The y values are staying the same. Right? If we have a y-axis reflection, the y values don't change. The point just goes from the right side exactly to that same y value on the left side. But what do we notice about the x's? The x's do change. For a positive on the right, we have its equal and opposite negative on the left. Okay, so that's something about the numbers that's happening also. So look at your rotational. Here we have 1, 2, right, as this point's coordinate. And then down here, it's -1, -2. Right, this one is 3, 0. This one is -3, 0. Okay, 5, -4, and -5, +4. So what can we say about these ones, x and y values? That they're the opposites, right? So we have a positive over here, gives us a negative over there, as well as your x and your y's. Okay, positive x, negative y, switches to a negative x and a positive y. Okay, so let's go to our notes page and make some generalities so we can write down some things about your reflexiveness when we have odd or even functions. Okay, what we're going to find is an even function has y-axis reflection, and odd functions have origin or rotational reflections or symmetry. Sorry, reflection y-axis symmetry or origin/rotational symmetry. So what can we say graphically about these even functions? What type of symmetry did they exhibit? Even functions have y-axis symmetry. y-axis symmetry, right? You can fold it right down the y-axis, and you're going to have the same on the left side and the right side. Where an odd function had origin or rotational symmetry. Okay, so you can use either words, origin or rotational symmetry, when describing the odd functions types of symmetry. Okay, so that's how we can notice which one is which graphically, right? You look at it, does it go down the y-axis? Does the y-axis split it into two? Or can you spin it 180 degrees, right? It's always a 180-degree rotation in order to have rotational symmetry. Now, what did you notice about the numbers, right? So these are the point values. Okay, so numerically, if we have an for every x comma y on the graph, right? For every x comma y, there is a corresponding what point? What happens to the variables? Negative x comma y. So for every x comma y that we have, for every point, right, and this is how we decide whether we have a point. For every point on the graph, there is a corresponding negative x with the same y value. Okay, that is an even function. Now, it takes a little bit more to describe an odd. Actually, no, it doesn't. For every x and y on an odd function, there is a corresponding with a D, corresponding negative x and negative y. Okay, so for odd functions with rotational symmetry, every point has an equal and opposite point on the other side of the origin. So the x changes signs and the y changes signs. Okay, and that's true for every odd function. Okay, so be able to look at a graph, or rather a graph, right? If you're shown a graph, we can decide whether it's even or odd, or if we're shown a table. Okay, if we're shown a table of functions, you can see if all the x's change, but the y's don't. That's going to make it an even function. Okay, so now let's get to the really good stuff, and that is the analytical stuff. So we know that a function is even, right? We know that the function is even if it behaves in this manner, if the equations come out to be like that. Okay, so we're going to look at the equations. We're going to analyze our equations. If the equation of the function, so what does this mean, f of negative x? What do we do if you want to find out what f of negative x is? Well, we're going to replace x in your original equation, okay, whatever one they give you. We're going to replace x in the original with negative x. Okay, and we're always going to replace it with parentheses. Always put it in parentheses so that you don't think this is subtraction, but rather a substitution problem. Okay? So you replace x in your original with negative x. We do all of your simplifying stuff from Algebra 1, and then we compare. Okay, we're going to compare our answer to what we started with. So that's what we're going to do. If you want to analyze this and say whether it is an even function, we're going to do this type of math. Okay? So example, is this crazy thing an even function? So remember, this is your original. This is the original function that you are given. Okay? So in order to test if it is even, we're going to replace x with negative x. So everywhere we see an x, we replace it with negative x. Okay, so let's start inside of your parentheses, or your absolute value. What is 3 times negative x? Negative 3x. So this is 2 negative 3x. And then what's negative x raised to the second power when I simplify it? That's the same as positive x squared. So a negative x raised to a power is the same as the positive. Okay, simplifying. Now, what can we do with our absolute value? What's the absolute value of negative 3x? It's normal 3x. So we can simplify by taking away the negative and writing our equation like this. Okay? So perform all of those simplifying operations in order to now compare. How does our equation relate or compare to the original? All right, notice that these are the same. And that will always be true in an even function. Replacing x with negative x does not change your equation. Okay, that's how we know that this is an even function. Okay, let's look at this example. 2x to the fourth plus x squared. Is this even? So we test by replacing x with negative x. Okay, so this is our first test. What we do all the time is we replace x with negative x. And now we simplify. Okay, so what do you remember about squaring, or rather raising a negative to an even power? Raising a negative to an even power is always a positive term. So negative x to the fourth is the same as normal x to the fourth. Negative x squared is the same as normal x squared. So we compare. How does our equation compare to your original? And we notice that they're the same, so we know that this is an even function because the original is the same as replacing x with the negative. Okay? There are your examples. Now let's look at this one. This one is looking pretty crazy. Right? We have x cubed over x minus 2x to the fifth. So we're going to look at a graphing calculator, and we're going to bring that graph in here so we can see what's going on. There we go. There's your function. So this is going to be an even function because it is symmetric about the y-axis. Right? I could fold this right down the middle, and I would have y-axis symmetry. So we have an even graph. Okay, so what about the equation? Let's look at the algebra. How does the algebra work when we replace x with negative x? So we have negative x to the third over negative x minus 2 times negative x to the fifth. Okay, so this is a matter of simplifying our problem here. On the top, negative x to the third is the same as negative of x to the third. And then we have our minus x. And what about this term? Right? This term is going to be a negative also, but what's a negative times a negative? A positive. So we have a plus 2x to the fifth. So when we compare these guys, notice that they don't look the same right now. Okay, but we know our graph is even, so we have one more part of simplification that we can do, and that is factoring out the negative from each of these terms. Okay, so we're going to pull a negative one out from the top, which makes this a positive x cubed, and we're going to factor a negative from both of your terms in the denominator. Okay, so the negatives cancel out, and now, does my original look like my new equation? Yes, it does. Okay, it should, because the graph is telling us that this is in fact an even function. So our equation had better verify what we believe from our graph. Okay, so there's some stuff about even functions, how we do that analytically. So now let's look at odd functions. So for an odd function, we have to do this. Okay, we're comparing two different types of equations. Okay, so once again, we are comparing. So we're comparing what happens when you replace x with negative x, just like we did a second ago. Okay, what happens when we replace x with negative x versus what happens when you make your entire equation negative. Okay, what does that look like when you make your entire equation negative? Those are the two things we're comparing to see if it's an odd function. Okay, so we're making x negative again, and we're also making the entire equation negative. That's what that means, negative f of x. Make the equation negative. Okay? So first thing is replace x with negative x. The same thing that we do to test for even. We replace x with negative x. So 3 times negative x, well, that's just negative 3x. And negative x cubed is minus x to the third. Okay, so of course, looking here, we notice that this is not equal. So of course, it's not an even function. Okay, if your f equals f of negative x, then we have an even function. So they're not equal, which means it's not even. So our second thing to do is to make the entire equation negative. Okay, put your negative out front and put everything in parentheses. Everything goes in parentheses. Okay, so now we have to distribute. We distribute to every term. We have two terms. The first term is 3x. The second term is x cubed. Okay, and how do we know that these are individual terms? Is there is a plus sign that separates them. Okay, a plus or a minus operation sign always separates your terms in your equation. So negative 3x minus x cubed, and now we compare to this one. And what do you notice about the purple equation and the blue equation? That these are equal. Okay, this means that we have an odd function. So this is your analyzing, right? We are analyzing this equation by replacing it first with negative x and then making the entire thing negative. Okay, so replace x with negative x. Right, we have a couple of x's here, so we're going to replace all of them with negative x. Okay, replace all the x's with negative x. And then we simplify. 2 times negative x is negative 2x. Here I have a negative times a negative. A negative times a negative is a positive, so plus x. And then I can go ahead and change this, right? A negative x in absolute value is the same as a normal x. So I'm going to switch that one right now. Okay, comparing, does that look the exact same as the original? Right? No, so we know that this is not an even function because your pluses and your minuses are different. So next, we make the entire equation negative. Make the entire equation negative. So how many terms are there again? Well, there's the 2x term, and there's the x root or x absolute value 2x. There are two terms. Okay, we know there's two terms because there's only one operation. So we're going to distribute to the 2x, and we're going to distribute it to this. Okay, I don't like to see when students do multiple distributions to places where they don't belong. Okay, you just distribute to every single individual term. And now we compare. Is the purple equation the same as the blue equation? Right, and hopefully you know that yes, it is. So our function is odd. Okay, because replacing x with negative x and making the entire equation negative do the same thing. Okay, so that's how we decide if it's an odd function. Okay, so first we test for even. Replace x with negative x. Okay, if that's true, then your graph is even. And if it's not, then we test for odd by making your entire function negative. Okay, and we compare these guys. Okay, so if it's even, these ones are the same. Your original and this one are the same. And if it's odd, those ones are the same. Okay? So let's analyze some graphs, or not some graphs, analyze some functions, decide whether they are even or whether they are odd.